Welcome to our presentation on theoretical and experimental results for planning with learned binarized neural network transition models. My name is Busar, and this is a joint work with Joe, Jacob, and Peter. To give a brief overview, I will start with a motivational example that is in the area of planning against adversarial agents. We control an agent whose purpose is to obtain a key to an initially locked door. In this planning problem and the others, we're not going to assume knowledge on the model of the planning problem. Specifically, we're not going to assume that we know what the transition function is. So in this specific example, this corresponds to not knowing where the enemy will move to as a function of our current location and our movement. In order to be able to plan with these learned BNNs, we're going to build on the existing data-driven AI planning formalism, which compiles the learned BNNs across the fixed planning horizon. And in the learned BNNs, let me remind you that the weights and the activation functions are restricted to 1 and -1. Given this formalism, we present new and existing optimization models to plan with these learned neural network models. We will present a 0-1 integer linear programming model and solve it with both branch and bound solvers and off-the-shelf pseudo-Boolean optimization solvers, that is, rounding set. We're going to introduce two new CP models and an existing weighted partial maxhead model. We proceed by presenting theoretical results on feasible planning with BNNs and show that it's NP complete. We do so by showing that the problem is in NP on a very high level, which corresponds to guessing the values of our actions and performing BNN inference, and showing that the problem is NP hard by reducing 3-set to the learned planning problem. Next, we show how to leverage model symmetry to derive no-goods. Here, we learn symmetrical no-goods from constraints that represent the learned binarized neural network function, lift, and apply it to other time steps. Experimentally, we will show that the PBO model that is solved by rounding set covers the most number of problems in least amount of time. Similarly, the ability to leverage model symmetry can speed up our base encoding from 1 to 3 orders of magnitude. Finally, we will conclude this presentation and present areas for future work. We start the technical portion of our presentation by giving a motivational example from planning against adversarial agent setting. In this example planning problem, the purpose of the agent is to escape the dungeon through an initially locked door by first obtaining its key. At the same time, the adversarial agent that is located on the bottom right corner of the maze will try to intercept our agent by the means of minimizing the distance with itself and our agent. Since we do not assume the knowledge on the adversarial policy of the enemy, one can try to ignore this policy and plan without it. In this example, we will see that the enemy will intercept our agent when we ignore the adversarial policy of the agent. However, if we learn this adversarial policy from, let's say, data, we can learn things like baiting the enemy and successfully plan with respect to the adversarial policy of the agent. Specifically, we're going to learn the unknown state transition function of our planning problem from data using neural network models. In order to be able to plan with respect to these learned neural network models, we're going to build on the previous data-driven AI planning formalism. Here, we will model our planning problem using factored state and action variables. In this work, we're going to assume that they have binary domains. We're going to assume the existence of a transition function that maps the values of state action variables onto the values of state variables in the next time step. We will assume the availability of big data that is in the form of state, action, and next state variable values. And we're going to learn the unknown state transition function t from data as a deep neural network model. We will sequentially chain the learned neural network models over a given planning horizon and optimize over our free action variables to maximize the total reward obtained by the planner. Here, let me remind you again that the weights and the output neurons of the learned BNNs are restricted to 1 and -1. This allows us to compile the learned neural network models into efficient mathematical optimization models, as we will present next. The first contribution of this paper is the new CP model. Given the learned BNNs, we're going to declare 3 sets of decision variables. The first set of decision variables, xit, will encode whether action AI is executed at time step t or not. The second set of decision variables, yit, will represent whether state variable si at time point t is true or not. Finally, this third set of decision variable, zilt, will encode whether neuron ul in layer L is activated at time step t or not. Given the definitions of our decision variables, we will next describe the constraints of our CP model. The first set of constraints will set the values of state variables at time step equal to 1. Next, we're going to enforce constraints on our state and action variables across all time steps, and enforce constraints on our state variables at the end of our planning horizon. We're going to map the inputs and the outputs of our BNN to the state and action variables of our planning problem. Then we're going to model the activation behavior of every binarized unit in the BNN, such that if the input is greater or equal to 0, we activate that neuron. Otherwise, the neuron will be deactivated, where the input to the neuron will be the weighted sum of the inputs from the previous layers, and the bias term can be computed to be a constant integer after the BNN is learned. Finally, the objective function of our CP model maximizes the total reward across all time steps. Our second CP model is a small modification on our first CP model, such that the decision variables that represent the activation and deactivation of every neuron, that is zilt, is replaced by a Boolean expression, which we note is similar to the work on training BNNs using CP models. Next, we covered the previous optimization models for solving the same planning problems. The first model we cover is a 0-1 integer linear programming model, which encodes the activation and deactivation of every neuron using 2 sets of big M constraints. Similar to previous work, we are going to be solving it using branch and bound solvers, as well as making use of the new advancements in pseudo-Boolean optimization technology. Namely, we're going to leverage pseudo-Boolean optimization solver that is rounding set. And finally, we cover the state-of-the-art encoding for optimizing these learned planning problems using weighted partial max set. Here, the reified cardinality constraints that represent the activation and the deactivation of every neuron in the BNN is encoded using an extension of cardinality networks. The second contribution of our paper is that feasible planning with BNNs is NP complete. We will show this by the problem is in NP n is in NP hard as follows. To show that the problem is in NP, we will first need to guess the values of our action variables for all time steps. Next, we need to do forward inference starting from the initial values of our state variables. Given that we have predicted the values of all state variables across all time steps, we can check whether constraints C and G are satisfied in constant time, which is sufficient to show that the problem is in NP. Next, we will show that the problem is NP hard. We will do this by reducing 3SAT to our learn planning problem, where we set the planning horizon equal to 1, and the input layer will have 2 action variables for each Boolean decision variable of the 3SAT formula, and we're going to have one state variable that's going to take the value of 1 if formula phi is satisfied, and 0 otherwise. We're going to construct a hidden layer with neurons where each neuron is going to represent a clause Cj uniquely, such that it will be activated if and only if that clause is satisfied. Finally, in the output layer, we're going to predict the value of the state variable such that the state variable is going to take the value of 1 if and only if formula phi is satisfied. Next, we need to decide on the values of the weights as follows. We're going to set the weights that connect the pair of action variables that represent Boolean variable Zi to the hidden unit that represent clause Cj to 1 and -1 if that Boolean variable does not appear in that clause, meaning the input from those pair of action variables are going to be cancelled out. Else if the negation of Boolean variable Zi appears in clause Cj, we set the weights equal to -1. And finally, otherwise, the weights are set to 1. Next, we set the weights between the hidden unit and the output unit all equal to 1. And this is sufficient to show that the problem is NP hard. The final contribution of our paper is the ability to derive symmetrical no-good constraints. We note that the BNNs across different time steps are symmetrical except their initial state and goal state constraints. Here we will learn no-goods from the BNNs and their respective constraints on their input using unique marker literals. And we will apply these derived no-goods that are learned at some time step across different time steps on our optimization models. To test the experimental effectiveness of our contributions, we have conducted 2 sets of experiments. In our first set of experiments, we have tested the effectiveness of solving the learn planning problems with different optimization models and solvers. Then we tested the effectiveness of different symmetrical no-good derivations. In our first set of experiments, we compared different optimization models on the existing benchmark domains with a 1-hour time limit. We found that the PBO model that is solved by rounding SAT performed the best by closing all the benchmark instances within the time limit while requiring significantly less amount of time. When we compared the CP models against the previous state-of-the-art model, which is weighted partial max SAT, we observed 1 to 2 orders of magnitude runtime improvement. When we compared the CP models against each other, we have observed a similar runtime performance. And finally, when we compared the PBO model with the previous state-of-the-art, we have observed 1 to 3 orders of magnitudes decrease in runtime. Similarly, when we compared the PBO model with both CP models, we have observed 1 to 2 orders of magnitude decrease in runtime. And here we conclude that the PBO model performed the best among all other models and encodings using rounding set. Next, we test the effectiveness of deriving symmetrical no-goods compared to the base model. Here we find that we test two different ways of deriving symmetrical no-goods. All is the case where we add all learned no-goods from our derivations, and propagate is the addition of no-goods that lead to immediate failure. Here we have seen that both symmetrical no-good derivations perform better compared to the base model. When we compare the base model to different no-good deriving strategies, we see that both symmetrical no-good derivations perform better compared to the base model again, by 1 to 2 orders of magnitude. And finally, when we compare different no-good derivation strategies, we find that all performs better on smaller instances while covering one less instance overall. So here we conclude that deriving no-good constraints that leverage model symmetry improves the runtime effectiveness of our mathematical optimization models. To conclude, we have shown that feasible planning with learned BNN models is NP complete. We have introduced two new CP models to solve this problem. We have shown that the PBO model that is solved with rounding set performs the best. And we have shown effective symmetrical no-good strategies to solve the problem. And finally, for future work, we're planning on studying related problems such as BNN verification using pseudo-Boolean optimization technology.